Hello everyone. I'm Zhijun Chen. Today I will introduce the concentration of random feature matrices in high dimensions. This is a joint work with Professor Hayden Schaefer and Professor Rachel Ward. The main goal of our work is to analyze the concentration of the spectrum of a symmetric rectangular random feature matrix A. I will introduce the definition of this matrix later. The analysis will lead to bounds on condition number of the matrix A and will be helpful in studying the random feature regression problem and binding its generalization error. In our work, we derive bounds for concentration of the Gram matrix A transpose A or AA transpose to the identity matrix or its expectation, which is a kernel matrix. Statistical dependencies on number of data samples, number of features, and dimension are obtained by leveraging matrix concentration inequalities with separation conditions on data or feature weights. Our main result is we show that under some mild conditions on data samples, feature weights and dimension, all singular value of the random matrix A concentrate near their full expectation and near 1 with a high probability. I will present the formal statement in the main results slide. Before going into our work, let me briefly mention some applications of random features. Since the expectation of the Gram matrix is a kernel matrix, random features can be used to approximate kernels and accelerate the training of kernel machines. This is desirable when evaluating kernel at data points is costly. It has been shown that random feature method can outperform traditional kernel machines in large-scale classification and regression problems. Another important application of random feature is a function approximation problem. They serve as an alternative to standard neural networks. The original least square regression may suffer from overfitting on noisy data. One solution to this is to introduce sparse regularization. The sparse random feature model can strike a balance between accuracy and training cost. There are many extensions of sparse random feature methods, and they have shown promising results. You can see discussions in these references. Finally, random feature method is also successful in kernel analog forecasting for dynamical systems. It can reduce the computation and storage cost while still be able to capture the important information from data. Now, will introduce the problem formulation. Let phi be a function of x parameterized by random variable omega. Here, both x and omega are vectors in Rd. In our work, we will focus mainly on the random Fourier feature, which is the complex exponential of the inner product of x and omega. Let f be an unknown target function we want to approximate, and omega 1 to omega n are drawn IID from a distribution rho. We want to find a linear combination of n feature functions parameterized by omega 1 to omega n to approximate the target function f using data samples xj, yj. Yj is the function value at xj, function value at xj plus some noise term ej. So the goal is to find the coefficient factor C sharp. This can be done by solving the following rigid regression problem. In the formulation, vector y is takes yj as its component, and A is the random feature matrix defined element-wise by the feature values at data point xj. The size of this matrix is M by capital N. The row number is the same as the number of data samples, and the column number is the same as the feature numbers. For elements on the same row, they share the same data point xj, and for elements on the same column, they share the same feature omega k. The spectrum of random feature matrix A will affect the property of the solution C sharp to the rigid regression. And the generalization error of our model is also related to the spectrum of matrix A. Here are some null results. Rahimi and Rashid first show that the linear combination of random feature functions are dense in a reproducing kernel Hilbert space with kernel defined by the feature function and sampling measures via Bochner theorem. This lays foundations to many applications of random features. Rudier and Osasco prove that under some assumptions of the spectral decay of the kernel, using square root m times log m number of random features is sufficient to achieve 1 over square root m learning error if the target function f is in the corresponding RKHS. The optimal risk of our model is obtained when it's over-parameterized. That is, we should use more features than data samples. In May and others, they stress the number of features we used capital N should be larger than M, which is the number of data samples, to 1 plus delta, or some positive delta, in order to achieve a better risk. In Ma and others, it is shown that when feature numbers capital N equals to number of data samples M, that we are in the interpolation case. And in this case, the smallest eigenvalue of the Gram matrix is close to 0. And this causes large generalization error and slow deterioration of gradient descent dynamics in training this random feature model. For sparse random feature model, it has been shown that the generalization error for threshold basis pursuit depends on the singular value of matrix A. The test error in random feature model also exhibits double descent phenomenon, which also suggests using a over-parameterized model can achieve better risk. It is shown that this double descent is related to the distribution of singular values of random matrices. You can see discussions in these references. These are numerical experiments showing the concentration of singular values of our matrix A. The first two figures show the distribution of singular values in ascending index. In these two cases, letter M is said to be 100, and capital N is 500 for the left one, and 5,000 for the right one. Data and feature weights are sampled from two Gaussians. We can see that singular values concentrate around 1 quickly in dimension. Singular values are within 0.5 to 2 when dimension D is larger than 8, which is shown by the blue curves in these figures. The concentration is more significant for large capital N. You can see the comparison of these two cases. On the right-hand side, you have more significant concentration. For the bottom two figures, we set letter M to be 100 and capital N to be 5,000. The left one uses weights sampled from Gaussian with small variance, and the right one uses large variance. We can see that the larger variance leads to more significant concentration of singular values. Note that in all cases, there is an asymmetry in the distribution of singular values around 1, which is due to the kernel matrix. Although the Gaussian kernel matrix is close to the identity, but it's not exactly the same. Here are our main results. The first is a theorem for concentration to kernel matrix. We use the following assumptions. We assume there exists a positive number capital R, that is the lower bound for the square distance between arbitrary two data points. And we assume weights are sampled from a Gaussian with variance sigma square. And if these two conditions hold, the first says the number of features capital N is greater than some constant times the number of data samples M times a logarithm factor of M. And the second condition is the sampling variance for weights sigma square is larger than some constant over the lower bound capital R times a logarithm factor of M. If these two conditions hold, then with high probability, the normalized gram matrix A transpose is close to its expectation, which this expectation is the Gaussian kernel matrix. These two are close in the sense of operator norm. The constant C appears in the first condition is universal. Next is a theorem for the case when both data and weights are random. Suppose that data xj are from a Gaussian with covariance matrix being a multiple of identity over dimension D. And omega weights, omega are sub-Gaussian with covariance matrix being a multiple of identity. If we have more data samples than features, that is when M is greater than capital N, we are in underparameterized regime. The matrix A is a tall matrix. And if these three conditions hold, the first says the dimension D should not be too small, but it only needs to be larger than the logarithm factor of capital N. The second says the variance product has to be larger than a logarithm factor of N. And the third says the number of data samples M should be larger than some constant times number of features capital N times a logarithm factor of N. If these three conditions hold, then with high probability, the normalized gram matrix is close to identity and also close to its expectation. Here, the expectation is taken with respect to both x and omega. The constant C1 appears in the first condition depends only on the sub-Gaussian parameter of the omega, feature weights omega. And this C2, the constant C2 in the third condition is universal. Let me briefly discuss the role of these three conditions played in this theorem. The first condition on dimension D is for the separation of feature weights vector. That is sub-Gaussian, the sub-Gaussian vectors in high-dimensional space are separated. The second condition ensures that the full expectation of the singular values are close to 1. And the third condition is from a matrix concentration inequality, which measures how far the grand matrix deviates from the kernel matrix or its expectation. And by the symmetry of the input variables, we also have a similar result for over-parameterized case when M is less than capital M. In this case, the matrix A is a fat matrix. We have these three similar conditions, and the role of M and capital N just switched. Now, let me give an outline of the proof of our main results. One may note that our random feature matrix A is similar to the bounded orthonormal system matrices commonly seen in compressive sensory. However, we cannot apply the results of BOS matrices here directly due to the following three reasons. First, feature weights for BOS matrices are fixed, and they are orthogonal to each other in L2 sense, while features here are random and do not form orthogonal system. Second, while BOS matrices have column independencies, we have neither column or row independencies for grand matrix or the random feature matrix A itself. This prohibits us from using many random matrices results directly. Third, we do not assume data to be bounded. Many analyses of BOS matrices typically assume the boundedness of data samples. Unbounded data has been a long-standing question for the analysis of some properties of BOS matrices, especially the restrict isometry properties. I will use the proof of under-parameterized case as an example. The main idea is to decompose the differences between the grand matrix and identity or its full expectation into these two terms here. And then we bound these two terms separately using different tools. For the first step, we consider the scenario that our weights are separated. That is, there exists a positive number capital R, such that the square distance between arbitrary two weights vector are bounded below by R times dimension D. Then in this case, we can decompose this term here into summations of rank 1 independent matrices. Applying matrix Bernstein inequality, we can show that this quantity is small with high probability. This quantity, exactly the first term, appears on the right-hand side in the previous slide. Step 2, we use a restrict isometry constant estimate for sub-Gaussian matrices. This is a result from compressive censoring. We use this result to show that when weights are sampled from sub-Gaussian distribution in high-dimensional space, they are separated with high probability. That is, they satisfied this condition for some capital R. The key takeaway here is that the second-order restrict isometry constant for a matrix implies some kind of orthogonality of its column vectors. Step 3, under conditions for the first and second step, we show that the following term, which is the second term on the right-hand side in the previous slide, we show that this term is small via direct bonds. Finally, we combine results from these 3 steps, and we can prove the theorem for underparameterized. The proof for other theorems are similar. Our main theorem improves our previous concentration results for random feature matrix in this reference. Specifically, our new result have the following improvement. First, if we rearrange the first 2 conditions in our main theorem, that is the conditions for dimension D and the conditions for variance product, we get an upper bound for number of features capital N or number of data samples M, depending on whether you in underparameterized the case or overparameterized the case. This upper bound is depends on the dimension and the sampling variance. Specifically, it is the minimum of the failure probability delta times the exponential of dimension D and the concentration parameter eta times the exponential of the variance product. Here we ignore the constants since they are not optimal in our theorem. From this expression, we can see that if we consider our problems in a very high dimensional setting, the first term is very large. So the bound for capital N or M depends essentially on the concentration parameter eta, not the failure probability delta. Well, in our previous paper, the bounds depends on the product of delta and eta for large D. Second one, the assumption used in our old theorem is that both data and the feature weights are IID Gaussians. Here we extend the results to the case when they are from sub-Gaussian distribution. And the sub-Gaussian assumptions only affects the constants appears in our bounds. It does not affect the general scaling condition. Lastly, we do not require our data to be independent or even random in our new results. This can be important since in some applications, one may not have IID random data, but it is possible to ensure they are separated. Finally, some remarks and conclusions. In our work, we show that the singular values of the random Fourier feature matrix concentrate around their 4 expectation and concentrate around 1 with high probability, provided some mild conditions on number of features capital N, number of data samples M, and dimension D are satisfied. So our random feature matrix A is a well-conditioned matrix in high-dimensional setting. In discussion of the sub-Gaussian weight case, the constants appears in our bounds depends only on the sub-Gaussian parameters. So as long as these weights are independent and their distribution have the same sub-Gaussian parameters, we allow them to follow from different distributions. So this is another extension of our results. In our previous work, we also give the condition for random feature matrix A to have a restrict isometry property. And we believe that the techniques used in this work will be helpful to extend that result, especially in studying the dependencies of IP bounds on dimension D. And we are also interested in the case when feature weights omega are on low dimensions. That is when feature weights omega are random sparse vectors. We are currently working on to extend our results for sparse additive models. It will be interesting to see if we can have some similar results in that setting. And finally, our research is of this work supported by these grants. And here are some references we used in this talk. And thank you.